So our topic for today is concentrating on shear force and bending moments. Now in shear force and bending moments, what we're going to do first of all is to just look at the common terminologies, the key terminologies that are critical. Then later on, we go to the application. As per tradition, that's where we normally start from. So to begin with, what is a shear force? Now, when you consider a shear force, there are two ways of defining it. First, we consider it to be the sum of forces acting on one side of a beam, one side of a section, one side of a member that you're analyzing. It can also be considered to be, or rather, you can also define it as a force which can cause failure by shearing or by causing one section to slide over the other during failure. Or it may basically have that tendency. Similarly, when you talk about a bending moment, you're talking about a moment that has the tendency to bend a material or to cause failure by bending a material. But in our analysis, in our calculation, we'll be focusing on saying that this is a moment, or rather the summation of moments on one side of a given section, a beam, or whatever you are analyzing, whatever it is that you are trying to analyze. But then, when you're considering shear forces and bending moments, you don't end on the theories. You also consider putting them in form of a diagram. So you say, what is a shear force diagram? Now, a diagram, in this case, what we are calling a shear force diagram, this is a graph which is supposed to represent the variation of shear forces along the axis of a beam. So we're saying that a shear force diagram is a graph showing the variation of shear forces along the axis of a beam, a member, or a section, whatever it is that we are trying to analyze. In a similar way, when you consider what we are calling a bending moment diagram, similar definition, but this time around, we just talk about it from the bending moment side. So we're saying this is also another graph, which is supposed to show the variation of bending moments along the axis of that beam. Now, when you're doing your calculations, you need to know which one is positive, which one is negative, and things like that. So comes what is known as the sign convention. When would you say this moment is positive or negative? So for a positive moment, it's supposed to cause a left portion to slide upwards in relation to the right. Now that language may sound a bit strange. In practice, if you are calculating moving from the left going towards the right, all the forces remaining on the left acting downwards, they are considered to be negative shear. The ones that will be acting upwards, they are shear forces, which are positive. So positive shear forces will be acting upwards, whereas negative forces, shear forces, will be acting downwards. So in the end, you add them together and get the sum that you're looking for as you continue with your calculation. With the bending moment, you have a positive moment is supposed to be clockwise on the left portion or anti-clockwise on the right. Then we say this is a positive bending moment. In addition to all this, we also have what is known as a point of contraflexion. This is a point where the moment is transitioning, moving from the positive to the negative. So you draw a bending moment diagram. Then the point where the moment is shifting or changing from the positive to the negative, that is the point we call a point of contraflexion. Now, such a point, the time zone we may decide to ask you to calculate and locate where it is. So you may pick a variable and say that at that point, your x is supposed to be equal to 0. The moment at that point should be equal to 0. Then you plant the various variables and parameters and you calculate. It will give you the distance at which that changing from positive to negative is taking place. So in other words, we are saying, if you are talking about positive and negative almost meeting, then you're talking about a neutral point, which is 0. So that's why we say at such a point, the moment is 0. So picking from there, then you can say, we'll pick from that transitioning, then you can make out your own calculations. Now, there is also what is known as the application package. How do you apply this information? Here we have a beam, total length 11 meters. Now in this 11 meters, as you can see, you can decide to add all of them. There's 3, 2, 2, 2, and 2. Basically, you're simply saying 8, then add 2 to the 8. Rather, add 3 to the 8, you have the 11. So that is the total distance, which is 11 meters. Then what do we need to find? We need to calculate, first of all, the shear forces, and then later on the bending moments. We want to draw. The question is asking us to draw. Now, let's not get this wrong, because when it's asking us to draw, you cannot start drawing straight from there. You need to calculate the values of these shear forces, then later on the bending moments. Then the values that you accrue are the ones you use for the drawing. Well, let's do this. Here, you will not proceed to the calculation of the shear forces if you do not know what the reactions are. As long as you have unknown variables, the calculation becomes vague, it will be incomplete, and you will not be able to proceed with your analysis. So our starting point is to first calculate these reactions, R1 and R2. So that's where we're starting from. So in this case, we're going to take moments about this point, which is R1. And then we apply the principle of moments where we say summation of anti-clockwise moments should be equal to the summation of the clockwise moments. So if you check carefully, you'll notice that by inspection, you will notice there's 50 multiplied by 2. 50 multiplied by 2. Can you see the direction? It's moving like that. So already telling you that such a moment is actually clockwise. The same thing with 40 multiplied by the distance up to where R1 is. We're talking about the distance from point D, where the 40 kilonewtons is acting, up to point B, where R1 is acting. That distance is the sum of 2 and 2. 2 plus 2, giving us a 4. So 40 times 4. So this also is yet another clockwise moment. And the last clockwise moment is 5 multiplied by the whole of the distance up to our fixed point. So this is basically 5 multiplied by 2 plus 2 plus 2 plus 2. It's like 2 multiplied by 4. So 5 multiplied by 8. The total distance here is actually 8. So this is what we have then. Now, on the other end, we also have the anti-clockwise, which is 10 multiplied by 3. Remember, we're not going to change anything. We're still taking moments about R1. The same thing with R2 multiplied by this distance, which is 6 meters. So this gives us that direction. So giving me 10 times 3, this is an anti-clockwise moment. R2 multiplied by 6, this is a clockwise moment. Then on the other end, I have the clockwise moments, which, like I said, we have 50 multiplied by 2, this one, followed by 40 multiplied by 4, which is this one, 40 multiplied by 4. And lastly, I have the 5 kilonewtons multiplied by 8. Let me go through this again. We are taking moments about R1. How would I know whether this moment about R1, for example, the moment created by the 10 kilonewtons, how would I know whether it's clockwise or anti-clockwise? It's very simple analysis. All you do, just ignore the other forces. Consider that this beam is only having this force and it's pushing downwards. What would be the direction of rotation of this beam being pinned at B when this force is acting down like that? You will notice that this beam will be forced to rotate like that because of this force, or moving in that way. So this is your anti-clockwise direction. The same thing with this one. Suppose this is we're still taking moments about here. This is your fixed point. This force is acting downwards. If considering this force alone, the kind of reaction, the kind of movement, the kind of rotation it would cause, as long as it's acting in that direction, would be the beam going down, meaning rotating in this direction, which is clockwise. So that's why we start. Here I have my anti-clockwise moment. The first one is 10 by 3. The similar one is reaction to R2 multiplied by all that distance. R1 is not involved because its distance is 0, so it's eliminated in this calculation because we are taking moments about R1. Hence, it cannot appear here because its distance is 0. So 10 by 3 added to, then I have R2 multiplied by the whole of this distance, which is basically R2 by 6. Let me go to the clockwise side. The clockwise one, the first one is 50 by 2 added to the next one, which is 40 times 4. And lastly, I have 5 multiplied by 8. That's how these are coming up. What you do after this is to make R2 the subject, where you calculate what is here, multiply all that, and the end result is 45 kilonewtons. Your R2 is 45 kilonewtons. If I want to find R1, I have two options. I can decide to take moments about R2, or we go by this. Summation of upwards forces is equal to summation of downwards forces. Because I already have one of these forces, I'm only missing one of them. Either method I decide to use, the answers will still be the same. So here I've decided to pick summation of upwards forces is equal to summation of downwards forces. Summation of upwards forces is equal to the sum of downwards forces. What are we saying here? We're saying that if I add the forces that are acting upwards, I add them. They have to be equal to when I add those that are acting downwards. All of them added together should be equal to those acting upwards, also all of them added together. So what am I saying? R1 plus R2 should be equal to 10 plus 50 plus 40 plus 5. So R1 plus, my R2 was found to be 45. So hence R1 plus 45 is equal to 50 plus 10 plus 50 or plus 40 plus 5. These are the 4 downwards forces. These are the 4 downwards forces you can see here. The next, all you are doing now is make R1 the subject of the formula, which gives me R1 being equal to, the 105 will be there, then I'll subtract the 45 coming to the other side. What I get now is 60 kilonewtons. Remember, you do not need to struggle with the kilos. Leave them like that. Because Even your answers will also be expressed in kilos like that. So I have my reactions. Now here I'm emphasizing that do not rush to the working, because if these reactions are wrong, then it means that even your working will also be wrong. So make sure here your answers are correct. Then you end up with correct values as well. So that's how you proceed. Now, having found the reactions, let's go now to the shear forces. So our starting point will be the shear forces. Then we'll proceed to the bending moments. This is the diagram we're dealing with. A, B, these are the important points where the forces are acting. When you're dealing with shear forces, where there is no force, it means the shear force is the same. A to B, you have the same shear force. Now here is where we'll bring back the sign convention. So shear force. If I look at A to B, I'm talking about the distance from 0 to 3 meters. Here, I'm standing at point B. If I say A to B, I set my foot at point B. That's where I'm stepping. When I look back, the only force remaining on my left-hand side, here, there's only one force, which is 10. Now, this one is acting downwards, telling me that according to the sign, as long as it's acting down, remaining on the left, then it's negative. Therefore, for this one, what I have is negative 10. So hence my negative 10 there. Let me repeat this. B to C. This time, I'm setting my foot at point C. This is where I'm standing. This is where I'm stepping. This is where I am right now. Then look back at what has remained on the left. What do I have? I have R1 and 10. R1 is acting upwards. 10 is acting downwards. And remember, R1 was how much? We got 60 kilonewtons. So I have positive 60 because it's acting upwards, and negative 10. What should I do with the two? I add them. Negative 10 plus 60. That's my answer. I proceed to CD. C to D. Again, I'm at point D being my last point. Looking back at what I've left on the other end, I have 50, 60, 10. 50 is acting downwards, so it's negative 50. 60 is acting upwards, so it's positive 60. So therefore, I put them together. I have negative 10 plus the 50. I've only included the newcomer, negative 50. When you add them, your answer comes out as 0. Let me go the same way from D to E. D to E. Once again, I'm stepping here at point E. What is remaining on the left? What do I have on the left-hand side? There is only one new member, which is 10. The rest are replicated. So I have negative 40 because it's acting downwards. Negative 50, also downwards. I have positive 60 because it's an upwards force. Then also there is negative 10. That's how I'm going to proceed to add them. Negative 10 plus 60 minus 50 minus 40. And my answer is negative 40. Lastly, I'm moving to this last portion, which is E to F, meaning that I put my foot at point F. Looking back, there's a newcomer here. Our newcomer is actually 45 kilonewtons, the one we found for R2, and it's an upwards force. So what am I going to do with this one? I'll just add it to the list. The rest, I will reproduce these the way they were, but I include the newcomer. So I have negative 10, positive 60, which is this one, negative 50, negative 40, with now the new entrant, the new entry, which is positive 45. My answer is 5. So here is where I say that if you got it right, you should be able to get the answer which we have here. The number which is here should be your last answer. Because if you have to start calculating starting from here, going backwards, this will be your first answer. Don't worry about the sign convention, that's the correct signage. This is how you handle the shear forces. What about the bending moments? Let's bring back the same diagram. With bending moments, you respect the distances. So you're going to move point by point. So I'll start with point A, I'll go to point B, C, and so forth. Look at point A. When I'm standing at point A, my distance from the left is nothing, so it's 0. So I have negative 10 by 0. The sign convention is not supposed to be your stress because the forces that the forces that were negative remain negative. We'll use them like that. So for point A, it's 0. When I talk about point B, it means I'm now here. So this is my new fixed point. So I have negative 10 by 3. Negative 10 multiplied by this perpendicular distance, which is 3. So my answer is negative 30. Can I repeat this? Now this time going to point C? Yes. When I come to point C, I have negative 10 by the whole distance. Now we have shifted, our new fixed point is here. So we cannot ignore the distances. We have 3 and 2 giving us a 5. So I'll have negative 10 by 5, then plus this 60 by this distance, which is 2. So then 60, which is positive, multiplied by 2. So negative 10 by 5 plus 60 by 2. My answer is 70 kilonewton meters. What if I try the same with point D? Point D is now giving me the 3 forces there, each of them now creating moments. Negative 10, its new distance up to point D is 2 plus 2 plus 3, which is 7. So I have negative 10 by 7, positive 60 by 4, because these are 2 and 2. Then the newcomer is negative 50 by this distance here in between, which is 2. So I have negative 50 by 2. You enter all that in your calculator, you should get 70. What if I proceed now to point E, which is this one? With point E, what I have now, negative 10 has a new distance, which is 2 plus 2 plus 2, 6, then add 6, 3 to the 6, you have a 9. So I have negative 10 by 9, because the whole of this distance up to our new fixed point is 9 meters. So negative 10 times 9 plus 60 by the distance in between, which is 6, positive 60 by 6. Next, I have negative 50 by what distance? Of course, we add this one and that, meaning negative 50 by 4. And lastly, I have negative 40 by this distance here, which is 2. And those are the numbers we have. The negative 10 by 9 plus 60 by 6 minus 50 by 4 minus 40 by 2. The answer is now negative 10 kilonewton meters. Let me get to the last one. Point F. This is again your checkpoint. When I'm at F, my new distance for this is now 11 because it's all this up to there. So that's why I have negative 10 by 11. 60 is now by 8. Then negative 50 by this distance here, which is 6 meters. 2, 2, 2. Let's include the 40 by a new distance, which is now 4 meters. And lastly, I have R2, which was actually 60, rather 45. So positive 45 by 2 meters, because where this is acting and where the F is, it's just 2 meters. The answer I get is a 2. Again, this is your checkpoint. In case you get it wrong, it means this part will not give you a 0. So you have to counter check your working, look at the numbers you put there, look at your reactions. At least it will give you a clue as to where things went wrong. Now that you have calculated your shear forces and bending moments, you can now start your drawing. Your drawing of the shear force and bending moment diagram starts with copying the question, that diagram in the question the way it was. So we reproduce it together with all the points A, B, C, D, E, F, and the forces planted there so that we can identify the key points. You can also decide to include the distances. This is 3 meters, 2, 2, 2, 2. That's okay. So after you've copied that, then you start with this straight line. Where do you put this horizontal line representing the axis of a beam? You make sure the biggest distance is accommodated there, which is the 50, the positive number. The biggest positive is 50, the biggest negative is negative 40. So you have enough space up there. And then you start. What was your answer for A to B? It was negative 10. So you mark out negative 10 going downwards. And you draw just a straight line for negative 10. And you label your negative 10 like that. Negative 10 kilonewtons. This is your 0. Up here, this is your positive region. Down there, that is your negative region. Going up, B to C, this is where you had 50. So you measure out the 50 moving from there all the way up. How do you do this? If you want, you can use the scale that is reasonable. You can decide to use a scale, or you can use something that makes sense. For example, what I put up here, what I'm putting up there should be at least something similar to 5 times this. Or it may not need to be highly accurate, but it should be able to represent the numbers as they are. So this is my 50 going up. C to D, the answer we had was 0, so we don't put anything there. D to E, it's negative 40. So I measure negative 40 moving from 0 coming down, and I just draw a line. Because here we say D, where there's nothing, it means the shear force is the same. The final portion is 5. So I measure from 0 going up by 5. Remember, this is 10. When I compare this 10 to the height of the 5, I should have at least half of this is my height there. So then I draw a line representing the 5 kilonewtons and I write the 5. When I'm done with that, then I just now bring up the boundaries, closing up the diagram. Even here, I drew a straight line covering there. So another one, and now just a vertical line. So this is my shear force diagram. What you see here, these hatch lines are not mandatory. If you have enough time, you can include them. But if you don't include them, it doesn't affect anything because someone is able to see the diagram. For the sake of making it look neat, that's why we do this. But otherwise, there's no harm if you don't draw those lines like that. Lastly, we need now the bending moment diagram. You do the same. Look at the numbers that you're having. I have 70 as my biggest positive, negative 30 as my biggest negative. My biggest positive is 70. So what do? I leave enough space there. And then I just draw a straight line running there, representing a neutral axis, or the axis of the beam. So then I check my answers. What answer did I have for the bending moment at point A? It was 0. So I put a dot there. Next, what answer did I have for point B? I had negative 30. So I measure out negative 30. Remember, the scale I'm using now is for the bending moment. It may not necessarily be something similar to that, no? Because the numbers on the bending moment, the way they are behaving is different from the way these are. So here I have my negative 30, meaning from 0 going down, this is my 30. I just put a dot there. Next, point C, I had 70 kilonewton meters. So I measure out, this is my 30, meaning my 70 moving up there should be at least double this. So I measure out, this is my 70 here. Repeat the same for point D. Point D, I also had 70 kilonewton meters, so I just put a dotted line there. Then I also have point E where I had negative 10 kilonewton meters. I dot a line there also. How do I do it? Again, I just measure out from 0 going down negative 10. So this is my negative 10. But the last one, which is F, took me back to 0. So I dot again the 0 there. Once you are done with the dotted lines, you can now bring up your ruler and start connecting them with straight lines. From A to B, a straight line. From B to C, another straight line. From B to C, this dot from what I dotted there. So a straight line going all the way to point C. Again, from C to D, another line. D to E, another line joining them, just like that. Then E to F, another straight line. Remember, use your instruments. Again, once I'm done with this, I may decide to hatch or put those lines inside, or I may not do that because the boundaries are clearly seen. So this is my bending moment diagram. You don't need to put initials. You can write it in full on the side. This is the shear force diagram, and this is a bending moment diagram. So this is how you draw your shear force and bending moment diagrams. Now remember that this process requires you do a bit of some practice and then you enjoy it. Because if you just look at it without attempting to practice, then it's not going to, you can easily make a lot of mistakes and you will not be able to do it. But the moment you practice, you refine and even find easier ways of doing that. If it's in an exam where you've been given graph paper, you easily do this on a graph paper because this has already been drawn for you. You already have those lines and you're able to just pick them and you plot your graph. So as we practice, there's an exercise for this, but what if you have a scenario like this where you have point loads as well as uniformly distributed loads, UDL, which could be something like that or something else. How do you handle such? In the next video, we're going to have an analysis of that one, where you are now attempting to look at a case where you've been given a uniformly distributed load mixed with point loads. For now, thank you very much for your attention. I value your comments. Please keep those comments flowing and remember to subscribe so that the next one I'll post, you'll quickly see an alert.